Center for the Ethiopian Educational Information and Communication Technology presents Educational Satellite Television Programs.
Hello, teacher. Hello, students. Welcome to the first lesson of our second unit on acid-base equilibria. During this unit, we will study concepts of acids and bases as formulated by Arrhenius, Bronsted, Lowry, and Lewis. We will learn about the dissociation of water as well as weak monoprotic and polyprotic acids and bases. We will also solve different equilibrium problems, and we will explain how buffering actions affect our daily lives. We will use qualitative terms to predict whether a solution of a specific salt will be acidic, basic, or neutral. We will also learn how to solve problems involving concentration and pH of acid-base titration. Let us start today's lesson by learning about the Arrhenius concept of acids and bases, which is known as the classical concept. We will define acid and base in terms of this concept, and we will look at some examples. We will also explain why protons are bound to water molecules exist as H3O+ ion in aqueous solutions of acids. As we have discussed in grade 10, savant August Arrhenius was a Swedish chemist in the late 1800s to early 1900s. In fact, Arrhenius helped to lay the foundations for modern chemistry. According to Arrhenius's theory, the dissolved chemical compounds in electrolytic solutions are dissociated into ions. This occurs even when there is no current flowing through the solution. Arrhenius also stated that level of dissociation increases as the solution becomes more dilute. His theory turned out to be true only for weak electrolytes. This theory of electrolytic dissociation became generally accepted, and it also became a cornerstone of modern physical chemistry and electrochemistry. Arrhenius defined an acid as a substance that releases a hydrogen ion or proton or a hydronium ion in aqueous solution. Some examples of Arrhenius acids include hydrochloric acid, nitric acid, sulfuric acid, hydroiodic acid, hydrobromic acid, and hydrofluoric acid. A substance should also contain ionizable hydrogen in order to be called an Arrhenius acid. Let us look at an example. When hydrochloric acid dissociates, it forms a hydrogen ion and chloride ion, as shown by this question. When hydrochloric acid dissociates in water, it forms a hydronium ion and chloride ion. This can be represented by this equation. Students, in the 10th grade, you learned about the limitations of this definition. Can you recall what these limitations are?
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back, students. You were correct to say that the Arrhenius definition of an acid is limited because it only explains the behavior of acids in aqueous solution. Also, this definition does not explain why some substances display acidic behavior in the gaseous state and in non-aqueous solutions. If you answered that activity correctly, well done. Arrhenius defines a base as any substance that ionizes or dissociates in aqueous solution to release hydroxide ion. Examples of Arrhenius bases are mostly ionic metal hydroxides, such as lithium hydroxide, sodium hydroxide, potassium hydroxide, and barium hydroxide. Let us look at a couple of examples. When sodium hydroxide dissociates, it forms sodium plus and hydroxide ion. When barium hydroxide dissociates, it forms barium 2 plus and 2 hydroxide ions. In pure water, most molecules exist as H2O. However, a small number of molecules are constantly dissociating and reassociating. Pure water is neutral in terms of acidity and basicity. This is because the concentration of hydroxide ions is always the same as the concentration of hydronium ions. An Arrhenius base is a molecule that increases the concentration of the hydroxide ion when it is dissolved in water. While chemists often write H plus and refer to the hydrogen ion when they are describing acid-base reactions, the free hydrogen nucleus, which is a proton, does not exist alone in water. This proton exists as a hydronium ion by reacting with water molecule. Students, in a moment, you will see a list of chemical equations. Based on their dissociations in water solution, classify each of the following compounds as Arrhenius acid, Arrhenius base, or as a compound that cannot be classified as either.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello again, students. Were you able to correctly classify each chemical equation? Let us go through them together now. Equation A is an Arrhenius acid. Equation B cannot be classified as an Arrhenius acid or as an Arrhenius base. Equation C and D are both Arrhenius bases. Students, let us finish our lesson by discussing some common household substances that contain acids and bases. Acids are found in a lot of things we see in our daily lives. Food products, for example, contain many acids. Citrus acid is found in citrus fruits. Tannic acid is found in tea, and lactic acid is found in a lot of dairy products, such as milk and yogurt. Acids are also used in batteries. They are used for pickling, and they are used in certain drugs. Bases are commonly used in cleaning products that you might find around your home, such as bleach. Both acids and bases are also used to produce a number of chemicals, such as fertilizers, in petroleum refining, synthetic fibers, and explosives. In today's lesson, we learned about the Arrhenius concept of acids and bases. We defined acids and bases in terms of his concept, and we looked at some examples of each. We also learned about how hydrogen ions release from acids and bind themselves to water molecules, and how hydroxide ions release from bases in water solutions. This brings us to the end of our lesson. Until next time, thank you, teacher. Thank you, students.